Hi folks, and welcome back to Physics with Captain Rod. This video is going to be the first of a two-part series on numerical integration. So what we're looking at here on the left, we're going to take a look at the curve y equals x squared. I like to use just nice simple functions when I go through examples so that we don't add needless complication here. And the idea is we want to be able to calculate the area bound between x equals 2 and x equals 6. So we're talking about this area right here. And again, what I'm going to do is talk about a numerical calculation. Now, I've already got a second window open over here on Microsoft Excel because in part 2 of this series, I'm going to use Excel to do the numerical calculations. So, all right, let's talk numerical setups. For starters here, this area question has a lower bound of x equals 2 and upper bound of x equals 6. So I'm just going to write this over to the side here. I'm going to use A to represent my lower bound, B to represent my upper bound. And when you're talking about area, the first thing we need to consider is what type of geometries to divide this up into. And one of the most common geometries is the rectangle. Now we can also break this up into trapezoids, but I'm going to save that for another video here. I'm going to use rectangles in this video. And the width of the rectangle is what I'm going to call delta x. Now, if I were to break this problem into two rectangles, each of those rectangles would be a width of, 2, because the distance from here to here is 4. If I break it up into two rectangles, each will be a width 2 here. You can always get the width of the rectangles by taking the upper bound, subtract the lower bound, and divide by the number of rectangles. Now here, what I'm going to do is I'm going to just put n here for the number of rectangles. I'm going to leave that decision to be made later. N could be 5 rectangles, it could be 10 rectangles, it could be 100. If we just leave this as a function of n, we can make that decision at a later point in the problem. Now, when you're working on a numerical setup, you have to be very mindful of how the rectangles are set up. And let me talk about some different examples here. Here's one possible setup. I could say, all right, here's my first rectangle. Here's my second rectangle. Here's my third rectangle, etc. I could draw a bunch of them. You'll notice, however, that in each case, if I calculate the area of this rectangle, I'm missing this little piece here. And when we do the second rectangle, we're missing this little piece. And the third one, we're missing this little piece, and so forth. So if I calculate the area of each of these rectangles and I add them all up, I'm going to get a number that's going to be a little bit too small because of all those missing chunks. Another possibility is we could draw these rectangles maybe like, oops, go back to black here, like maybe this. And I'm just going to draw maybe 3 of them. And again, etc. Now, in this case, if I were to calculate the area of that first rectangle, I'm going to be including this piece here, which isn't actually under the curve. And if I do the second rectangle, I'm including this one. And if I do the third rectangle, I'm including some area here. Every time we calculate an area of that rectangle, we will be including area that isn't actually bound under the curve. If we add that all up, we're going to get a number that's a little bit too big. Now, that doesn't mean that it's bad, but what we'd be getting is what's called an upper bound estimate. We'd be getting the upper bound estimate for the area under the curve. What I'm going to do is I'm going to go back and I'm going to set these rectangles up in a slightly different way. And I'm going to set them up, oops, so that the midpoint goes right through, or I'm sorry, so that the curve goes right through the center of the rectangle. You'll sometimes see this called the midpoint rule. I like to call it the Goldilocks rule, because here there's a little area outside the curve here that's included, but there's a little piece here that's not included. But you notice if I cut this and glue it here, I'm getting approximately the area bound under this curve. Same thing here, same thing here, same thing here. So we've got these 3 different ways we could set this up to get a lower bound estimate, to get an upper bound estimate, or this will give us an estimate that's kind of just right. And that's why I call this the Goldilocks method. There are other, even slightly better methods to use, but this is a pretty good method for just starting out with numerical work. Works pretty well. Now, you'll notice that in order to calculate the area of that first rectangle, we're going to need this height right here. I'm going to put that in green here. That height is equal to the function value at a very specific x, this x right here. When we do the second rectangle, we're going to need this height, which is the function value at this x, and then so forth. And by the way, I drew these rectangles kind of over exaggerated widthwise. I'm just drawing the first couple three and kind of exaggerating them widthwise so that I could focus on the setup. Now, you'll notice that we're never really going to need the 2 in this calculation, and we're never really going to need the 6 either. This is the first x value we see, or that we're going to need. And you notice that that value is 2 plus half of a delta x. You notice that the next one we need is equal to let's see, 2 plus, here's a delta x, and then another delta x, and so forth. So we're going to have to come up with some sort of way to get me these x values that we need. Also notice that in effect here, there's another variable that's introduced here. So I'm going to call this, the first rectangle. And this one's going to be the second rectangle. And then there's a whole bunch of them. The very last one would be the nth rectangle. Oops, I don't want to put that n right there. So you got to imagine the very last rectangle would look maybe something like this. So you see that there's this, what I would call, counting number that's introduced. The first rectangle, second rectangle, third rectangle. So I'm actually going to assign a variable to that. So I'm going to let I equal the rectangle number. Now, for each rectangle, we're going to need the x value, the appropriate x value to calculate a function value. So what I'm going to do is I'm going to come down here and I'm going to start kind of tabulating what I need here. We're going to need the I value, and this is going to be 1, 2, 3, and these are going to go down to n, no matter what value of n I choose. We're going to need what I'm going to call x sub I, and here's what I mean by x sub I. For the first rectangle, we need that x value right at the center. For the second rectangle, we're going to need this x value right at the center. These are the values I'm calling x sub I. So like, for example, x1 would be the x value at the center of the first rectangle. x2 is going to be the x value at the center of the second rectangle. x5 would be the x value at the center of the fifth rectangle, and so forth. And what I'm going to do is I'm going to write myself a little formula here that calculates that. Now, you notice that our lower bound is 2, so I'm going to start at 2. And look at what happens if I then add to that I times delta x. Now, 2 plus 1 times delta x would put us here. 2 plus 2 delta x would put us here. So see how we're starting at 2 and we're moving over 1 delta x, 2 delta x. 2 plus 3 delta x puts you at the right-hand side of the third rectangle. In general, this expression, 2 plus I times delta x, puts you at the right-hand side of the ith rectangle. Now, I don't want to be at the right-hand side. I want to be centered. Notice that to do that, we have to come back left half of a delta x. So in this formula here, I'm going to put a minus 0.5 times delta x. And what this will do is it will center my rectangle. Now, if I took a calculator and I just put values everywhere, I could calculate a number here, 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 all the way down to the nth one. Now later on, what I do in the second video here is I'm going to talk about how to set up Microsoft Excel to do all this kind of crummy math here, well, not crummy, but boring math for you. Now, I need to get rid of some stuff here. Let's see, I need a little more room. I'm going to get rid of this because I got more things to write. I'm going to take this now and move this over here. All right, now thinking ahead. In order to calculate the area of this rectangle, we need the height here. So I'm going to make myself another column, and that's going to equal f of x sub I. And again, in theory, this is some number, where this is my function. So the f of x sub I in this example is going to equal x sub I, whatever it is, squared. If this were maybe say a sine function, this would be sine of x sub I squared and so forth. This can be any basically any function at all. We're also going to need ultimately the area, which I would call a sub I, which would represent the area of the ith rectangle. In this example, the area of the ith rectangle is going to equal, boy, I need more room here. There we go. It's going to equal f of x sub I, which is a value that in theory we can calculate, times delta x. So these things are all now numbers that in theory we have. So for example, I've got a lower bound a and upper bound b. Once I choose a number for n, say 10, I could then calculate a delta x. I could then run through here, calculate all these x sub i's, maybe with a calculator. I could then take a calculator and calculate all the f of x sub i's. Then I could calculate the a sub i's, which would be the area of each rectangle. And then in the end, what we have to do is we want to add these all up. So a sub I is going to equal the sum from I equals 1 to n of all the, actually this would be a sub I. I got to go back and change that. I didn't mean a sub I. What I meant was the total area is going to be the sum of all the a sub i's. Now, with a calculator, this would be quite a little bit of work. And what I'm going to do here is I think I'll just stop this and make a separate video so this doesn't get too long of how to use Microsoft Excel to go through and do all these calculations for you. Before I do, however, I'd like to point some things out. All of this stuff like here, here, and here are all specific to this setup. If we had a different type of curve or maybe different bounds, or maybe we have another curve that we were looking for the area bound between them, there'd be more things we'd have to calculate. So your setups here, how you calculate the length of the rectangle like this and the area, is dependent on the type of problem and how you draw these rectangles initially. So the setup is very important for a numerical calculation. When you're going to use a finite value of n, like a finite number of rectangles, you have to pay very close attention to how these are drawn and how their setups are, because what will happen is, your equations will vary slightly depending on, or maybe even considerably depending on the original setup. Also, depending on the setup, you could be getting an upper bound or perhaps a lower bound. In this case, the way I've set this up, we should get a pretty good estimate for the area. So I'm going to go ahead and just stop that video right here and just make a completely separate run for using Excel to do all this numerical work. Have a great day.